So my name is Adam Granitz, and I want to welcome anybody or everybody who is watching this feed or will be watching this feed. And I have the extreme pleasure of having Gergo, Erdi, today with us, who is going to be talking about FPGA programming with Haskell. So with that, I'm going to hand over to Gergo. And just one last thing that I would like to mention is that if anybody has any question, right now you can only take those as comments on Twitter, or if you're watching the Twitch feed, you may comment there. I'm going to be monitoring both of those sources, and I'm going to pop those back in here for Gergo to answer. So thank you and enjoy.
Yeah, okay, thanks. So hi everyone. Yeah, so my name is Gergo, and I will be talking about a particular approach to FPGA programming with Haskell. And before I start, I'd like to mention that this talk is actually a second version of a talk that I already gave at the Haskell Love conference. But unfortunately, the recording of that talk is still not online. So my hope is that this way there will be a recording that people have an easy way of accessing, and two, I have more time here, so I guess I can go at a more leisurely pace and not have to rush through so many parts of it. So the title of this talk is Executable, Synthesizable, Human Readable, Peak 3, which is obviously a reference to the classic trilemmas. So the point is that I think that with Clash we can get all three of these. You don't have to choose any two and give up the third one. And basically what I would like to do is to convince you of this by looking in detail at an example. And our example is going to be the game of Pong, more specifically the solitaire version, so the one-player version of Pong. The two-player version wouldn't be any more difficult with this approach. The only reason that the main reason that it's for one player is that because then we can leave the two-player version as an exercise to the audience to go home and do it on their own time if they manage to pick up enough of the ideas from the talk. So Pong. So hopefully everyone knows Pong. Those of you who don't know Pong, well, I'm just glad that your parents let you attend this talk being so young. I think above a certain age everyone knows Pong. So the basic idea is that it's a very crude simulation of tennis, or I guess squash in the solitaire version. So you have a play field, and you have a ball that's bouncing around, and the playfield is surrounded by walls on three sides, and then on the fourth side there is a pedal that is controlled by the player. And the aim of the game is to hit the ball back so that it doesn't bounce out on the right hand side out of field. So what we're going to do is we're going to implement this game. We're going to make a solitaire game, and first as normal software. So we're going to make a normal Haskell program, and in this first section I hope that I am not saying anything new. So the whole point is that there should be no new revelations, no new surprises in this part, because the whole point of this talk is going to show that we can take the software implementation, and if we write that, with certain accommodations for a future hardware version, then we can in fact turn it into hardware. So for this first section, let's just think about how we would do a Pong game in idiomatic Haskell. So the way we're going to do that is we start with modeling the game state. So we'll have some data type for the state and some initial state, and then at regular intervals, in particular at the end of every frame, we will update the state by taking the user input and the current state and computing the new state. So what does the game state look like for Pong? Well, we're going to be using 10-bit signed numbers for coordinates. So the reason for that is because, first of all, we want a small screen, so a small resolution screen, to get that nice chunky retro look. So if you look at the original screenshot, like look at those pixels, right? These are nice big chunky pixels. So 10 bits might actually sound too much for that. And why is it signed? So the answer to both of these is that we're going to use 10-bit signed numbers because they make it easier to do the computation of the bouncing around. We will see what I mean by that. And it might seem strange that why is it a signed 10-bit number? Why can't we just use ints? So this is something where we kind of think ahead a bit, because we know that eventually we'll want to turn this into hardware. And of course, in hardware, the width of registers and the width of buses matters a lot. So we think a bit about that up front. And so we use 10-bit numbers instead of ints. So this is something that this is the one thing on the screen right now where we think ahead for a hardware version, but everything else is idiomatic Haskell code. Okay, so what is the state, right? So the ball has a horizontal and a vertical state, and both of these consist of a position of the ball and the speed of the ball. So we can imagine already that the way we're going to use it is at every frame we're going to change the position by adding the current speed to it to get the new position, right? And we're going to do it both horizontally and vertically. And the reason that is decomposed into horizontal and vertical components instead of, let's say, a position component of a 2-vector and a speed component of a 2-vector is that this way we will have an easier way of writing the bouncing logic, because then we can just write a one-dimensional bouncer and then use that both horizontally and vertically to get the intended behavior. And the other parts of the state, well, we have the Y position of the pedal, so that's the part that the user can move. And also, just to make it more like a game, like the difference between a toy and the game is that in the game you have a goal. So the goal here is to not let the ball fall, run off the field on the right-hand side. So if it does, we're going to mark that with this game over flag. And if game over flag is on, we'll flash the screen red for one frame to notify the user that actually the player that they've just lost the game, and then we can reset the game. And one thing you can see here is that we're deriving lenses for our state data type. And that's something that is, again, comes quite naturally in software Haskell. Like, why wouldn't you? If we're going to have a lot of code that goes into this state structure and changes parts of it, it makes sense to use lenses for that. But the nice thing is that we'll keep these lenses for the hardware version as well. So again, we do everything like we would do in normal Haskell. We derive a bunch of instances. We derive NF data X. That's a clashism. That's something that you just have to do. It basically just needed to simulate once we go to the hardware version. It doesn't really matter for us here. It's just you can just regard it as boilerplate that you have to derive NF data X without caring too much what it is. Yes, we just got this question actually. So NF data X is it's a clash. I'll get back to that once we get to the hardware version. I think it makes more sense once we get there. we can just not, I mean, for the software version, of course, we can just not derive it. The reason that we're driving it is because I want to use exactly the same code for software and hardware. Okay, so moving on. The initial state, well, we just pick some position and some speed for the ball. So we put it at 10 horizontal, 100 vertical, and give it some diagonal speed. We put the pedal basically at the half point, and you know, the player hasn't lost the game yet. And then to update the state, we need to know what our inputs are. So the inputs in this case is just two buttons, right? We have a button that moves the pedal up, and we have a button that moves the pedal down. Now, we could say that, well, you can't move the pedal up and down at the same time. The reason that we have two bools instead of something like a maybe direction is because this way we can put the logic of like physically, right? If you imagine two buttons, right? You can't press both buttons at the same time. It's a real, like, you can't say, oh, but you can't press both buttons. Well, I can with my two fingers. So we need some logic to decide what that should mean, and we want to include that logic in update state, basically, because that way we can reuse it for the hardware version, where, you know, the physical reality of the hardware is that there are two buttons. So even if here we pretended that we get something like a maybe direction, we would still need some place somewhere that turns two button states into such a value by, I guess, prioritizing one direction or the other. But if we do it this way, this logic will necessarily be implemented inside our game state modeling code. So once we have these inputs, to actually update the state, given such an input and given the previous state, well, we can see what we need to do at a high level. We update the ball position, so that involves, you know, adding the speed to the ball position, bouncing on walls and the pedal. Then we update the pedal based on the user input, and then we check if the ball is out of bounds, in which case we go to the game over. We set the game over flag. Okay, so what does update ball look like? Well, this is where we use the fact that we decompose the state into vertical and horizontal ball state, because then we can decompose update ball itself into vertical and the horizontal version. In fact, the horizontal version can even return whether we have hit the pedal or not, because we can make the game more enjoyable if we say that if the ball has hit the pedal, then we're going to nudge the ball based on the direction that the pedal has been moving in. So basically, if you hit the ball with a moving pedal, then you give it a bit of a, well, not a spin, because we don't store rotational momentum, but you can give it a bit of acceleration in that direction. Okay, and still, you can see that this is normal Haskell code, so it runs in a state monad, and the reason for that is because update state itself runs in a state monad. You can see this exec state call here, so that we can decompose the state-to-state function, or the st-to-st function, into multiple independent steps. In this case, we have the update vertical, update horizontal, and then the nudging. And you can also see that we use the lenses that we generated for st here to good effect when we change the second coordinate, so i.e. the speed of the vertical speed of the ball. Okay. Now for the actual bouncing, So if we think about this a bit, we can, like, this might look complicated, but once we get to the code version of it, it's actually very simple. So a reflective surface, we can model that as a point and the normal vector. So if the wall is at some point P, and we have just now updated our ball position from X node to X by adding its current speed to it. So this is the horizontal version. The vertical version is exactly the same, just rotated 90 degrees. So if we have computed our new X from X node, then there are two possibilities. So either X is on the far side of the wall or it's on the near side. So how do we know which one it is? Well, it's easy because we can just compare whether the distance between X and the wall is points at the same direction as the normal vector of the wall. If they do point in the same direction, that means that X is on the far side of the wall, which means we need to bounce it back. So what does it mean to bounce it back? Well, we can take the distance between X and the ball and the wall and reflect it over the wall to get X prime. Whereas if the distance is not pointing in the same direction as the normal vector, then we can then we don't need to do anything. Then X is already the new position. So what that means is that the code just looks like this. So we can write a function that, given a wall defined with a point and the normal vector, and the ball position, will tell us the new position of the ball and also whether it has been reflected or not. And then, of course, based on that flag, we can also update the speed in that direction, because when you get to the other, when you bounce back to the other side of the wall, that also means that your speed should flip. So the neat thing here is that we can do this by just comparing the signs of two numbers, because remember this, we decomposed it into horizontal and the vertical direction. So it's per coordinate. So for a single coordinate, we can check if a single, of course, this works because these walls are axis aligned. So we only have a horizontal and a vertical wall, right? Like two horizontal walls and one vertical wall. And the pedal also acts as a vertical wall. So we can use this to our advantage by simplifying the whole thing into just looking at the sign of two vectors. This is way more detail than we need to know here. I just thought it was neat that we can just do it this simply. Okay, so once we have this, so now we have basically everything to maintain the state of the game. So now comes the question of, okay, how do we turn that into something that the player can see? So the way we're going to do it is basically the shader approach, where we write a function from coordinates to color. So we say that the screen is a 256 by 200 rectangle, and for each pixel we compute the color. And of course this function is not just out there on its own, it's a function that also knows about the current state. So you can think of the type of draw as being parenthesized as state to a shader function from x to y to color. And color here is just a three tuple of red, green, and blue intensity. And then inside this draw function, given the state, we just write a bunch of predicates. So you don't see it here in this snippet, but you can imagine that is wall and is pedal and is ball is just some where bound variables. So is wall is just a comparison that either like y is, smaller than the width of the top wall, or, larger than 200 minus the width of the lower wall, or x is less than the width of the vertical wall, right? So it's just a bunch of comparisons, and same way, to compute if the given coordinate is the ball or not, we can just compare x and y to the x and y coordinates of the ball's current position. So, okay, so we do this, and of course we would like to see it in action. We would like to see it run interactively. And so this is where it pays dividends that everything we have written so far is normal Haskell code. So if it's just normal Haskell code, that means we can compile it and we can run it as normal software Haskell. So for example, we can take SDL2 to connect the events from a keyboard and into our stateful computation, and then the result, the result of applying draw on the state, we can then connect to the contents of a window. So here we see a very simple program where the important bit is that it runs in state t, maybe t.io, because the maybe t is used to exit the game. So you can see that if the escape key is pressed, we exit the game. It's not really part of Pong, right? It's just something we put here. It's like, notice that this is something we put in main. This is not something we put in the model of the game. But the important bit is that we in every frame we look at the state of the up and down keys as presented to us by SDL. So this key down function is a function from scan code to bool that is filled in every frame. And then we apply it on up and down key scan code to get the current state of up and down. Okay, so this gives us two bools, and we put these two bools into our input data structure. And we update the state that was initialized to the, the ball in the middle, blah, blah, blah. And then we apply this draw function on the state, which gives us, this x to y to color function. And then we have a small utility function, this rasterize pattern. So what it does is it takes such a function, like a shader or a pattern function, and rasterizes it into an SDL surface by just applying it on every possible XY coordinate pair. And then this is what it looks like, right? Now, of course, this is a bit unfortunate that it's so small. So 256 by 200 pixels. That's not a lot. But notice that in the code here we have this video params argument, and one of the fields of this video params is the screen scaling factor. And of course, if we increase that to like 4, then we get a nicer window that we can actually interactively play with. So, and there we have it. We have a game of Pong implemented in Haskell, and I would say that we have implemented it without too much effort. We really have just written it as we would have written it in normal software Haskell. So do we have any questions so far? And actually, I see that Adam has left the, okay. Yes, so the question is, what's the deal with these index types in draw? So, okay, so so basically to make computation in the state easier, we use 10-bit sign numbers in the state. But when we want to render it, we need to be, or well, we want to be a bit more precise. So the index type is basically, it's just a finite type with that many constructors. So index 200 is the type that has 0, 1, 2, and so on all the way to 199 as its 200 possible values. And we use that because in draw, we know that that's all we're ever going to get, because the size of the screen is like fixed and it's outside our control, right? Because it's the physical, well, in this case, it's not so physical because it is just a window, but we imagine it as being the full screen. We imagine it as being the whole world that we have access to. So the size of the world is not going to change. So these numbers we hard code on the type level. We will see some benefits to it. But one thing I can say already is that, for example, notice that here, or like in the video params, there's nothing about a window size. It's all determined by the types. So the fact that we use index 256 to index 200 to color as the type of draw, goes through rasterize pattern all the way to with main window, and then the types direct us to the right window size. But if we used index 200 and if we used index 256 in update state, it would be a huge mess, because if you look back on this, oh, actually I'm going in the wrong direction. I'm trying to go back to the, yes, this one. So notice that in the example where we do have a bounce, the x we get by updating x node is on the wrong side of the wall. So we need to be able to get out of the screen space internally for our computations. Like think about, like the easiest one to think about is the left-hand vertical wall, right? If you bounce off it, that means that you have a negative x coordinate temporarily. Yes, there's a question, so whether index is the same as fin. Yes, that's exactly what it is. So index is the same thing that's usually called fin in independently typed languages. Yes. So yeah, but so computing, like doing arithmetic with fin is super painful, and we need to extend the range anyway, so we might as well use some normal numbers, and it's also the reason that we use signed numbers, so that we can have negative coordinates temporarily while we are computing the reflection. I hope that answered the question. Okay, so now that we have this software implementation, so the whole, like, I haven't shown you anything new yet. So what's the point of this talk? Well, the point of this talk is that now we want to build a circuit that plays Pong instead of a program that runs on a computer that plays Pong. So we're going to use FPGAs for that. So a field programmable gate array, as the name says, it's an array of gates that can be programmed on the field, right? So what it means is that you have a collection of logic gates and registers, and the connections between them can be changed after the thing has been manufactured. So field programmable here means that the thing is inside some device, and you can just go on the field and you can go there and change its configuration instead of having to make a new chip. Because the only difference between different chips, if we abstract a bit, is in how their parts are connected. If you zoom in close enough on an integrated circuit, you just find transistors, right? But you can have two different chips. You can have like the chip you have in your washing machine, and you can have the chip inside your graphics card, and you have the chip inside the supercomputer. And if you zoom in close enough, they look the same. Well, the scales might be different, but the components are the same. So how come that they are different at the larger scale? Well, they are different because those small regular components are connected differently. So at an FPGA, those connections are electronically configurable. But what that means, in effect, is that you can make your own chips, right? Because if you can control how these components are connected, then you're doing then it has the same effect as if you connected them by designing a new chip. So the takeaway here should be that you can think of an FPGA as having your own chip fab. So you can manufacture your own chip with your own design, and then you can press a button, and now it's a different chip with a different design. So you have this FPGA, and then usually it has connectors to the outside world. If you get like a development board. So what we're going to do here is we're going to assume that we have some FPGA that is connected to two push buttons and also a VGA connector. And then we're going to connect that VGA connector to a display, and we're going to connect the two push buttons to the player's fingers. And then in between these, between the buttons and the VGA, we're going to put our own circuit, and that circuit will implement the behavior of Pong. And we're not just going to do it from scratch, we're going to do it by reusing basically everything that we have written so far for the software version. So let's see how we're going to do that. So the thing about FPGAs is that their programming tool chains are not nice. So there's two they're not programming languages. They are two hardware description languages, Verilog and VHDL. These two are the mainstream hardware description languages, and the tool chains that you get for your FPGA are usually fully closed and proprietary and whatnot. And so the only thing you can do is you can feed them Verilog or VHDL. But these are not nice languages, and the toolchains aren't nice either. So us functional programmers would like to use a nicer functional language. So why not Haskell? Haskell is Haskell is usually thought of as a software programming language. But if you think about a pure function, you can say that, oh, well, this could actually be the description of a circuit. Because you can imagine that the inputs to your function are the lines going into your circuit, and the outputs are the lines coming out. And because it's a pure function, it can be it's stateless. It really is like the outputs will just depend on the inputs. Of course, this doesn't yet tell you how you're going to make a stateful circuit. So this is where Clash comes into play. So Clash is a Haskell compiler that instead of compiling to an executable that you run on a computer, compiles to hardware description like Verilog or VHDL, which you can then feed to your FPGA toolchain or use it in your ASIC design process. But you, the programmer, write Haskell. So the way that works is that in Clash, there's a type constructor called signal, which is indexed by some clock domain to avoid accidentally crossing domains. But we're not going to care for that here because, like in this talk, all our designs are going to be single domain. And then for a given domain, signal DOM is an applicative functor, which tells you how you can combine it and how you can make stateless circuits. But also, there's this combinator called register, which takes an initial value and also a signal so the time varying value that will be used to compute its new value at the end of each clock cycle, and then it gives you a signal that is the result of feeding back that signal into it. So this is the so-called register transfer level model. So what we see in this diagram here is that the way it works is that we have some register, and the register is connected to a pure function, just a combinational circuit, which has some other inputs, but importantly, one of its inputs is the value of the register. And then the register also has a clock input, and whenever the clock ticks, the register value is updated to the result of applying the function on the input that comes in from the outside world and the current value of the register. And if you think about this, this is very promising, because this is exactly what we need for our Pong circuit, because we wrote our Pong saying that, okay, we have a function that updates the state, given some current input, by computing the new state from the old state, and we only want to run this once every frame. So this is exactly what we need to model Pong on the register transfer level. So the other thing we need before we can get to the actual circuit is how are we going to do video output. So we're going to use VGA, and the reason for that is, although VGA is obsolete in the sense that current day, basically it's an old analog standard that some displays, some TVs still support due to its legacy status, but no new hardware is really designed for it. But the reason we're using this is because VGA is very simple to understand conceptually, and because it's been used so much for decades, there's no shortage of support for it in displays and especially FPGA development boards. In fact, there are FPGA development boards where the output is HDMI, but the HDMI signal is generated by a custom chip that is fed a VGA signal from the FPGA, because generating a VGA signal is so much simpler. So what does VGA look like? So VGA is very simple. It's basically 5 lines. So 3 of them are red, green, and blue color channels. So these are analog. And then 2 sync lines, a horizontal and a vertical sync line. And basically, you fill the screen as if you were writing on a typewriter. So the electron beam starts at the top left corner and moves to the right at a certain speed. And then at the end of the line, the horizontal sync line tells the screen to reset and go back to the start of the next line. And then it goes to the right again, and then again the horizontal sync line goes up, and so it goes back to the start of the next line. And the timing of it all works, and then when it gets to the last line, the vertical sync line is asserted, and so it goes back to the top of the screen. And while this is happening, the color channels determine the color of the pixel that's currently being scanned. So if you're generating video signal, it involves 2 things. First, you need to generate the sync signals at the right timing. So everything works out only if the time between horizontal and vertical sync signals is correct. And by correct, I mean that there are various VGA standard modes, and each mode prescribes the specific timing requirements for these sync lines. But if you have that, then to produce a picture, all you need to do is to set the red, green, and blue output lines to the right value at the right time. So when you're generating the picture, you're just keeping count internally, like knowing how the electron beam will sweep the screen. So you're counting inside your head like 1, 2, 3, 4, 5. Okay, so now I'm at the 5th pixel of the current row, and I want the 5th pixel to be red. So now I want to put red, like, put red to its maximum value and green and blue to a very low value for the current pixel, because I want it to be mostly red. And then I keep counting. Okay, but now I've done this. Now it's 6. So, okay, so what do I want the 6th pixel to look like? So what does a VGA signal generator look like? Well, we can make a reusable one. I'm not going to show you the implementation of it. I just want to show that because of the powers of abstraction in Haskell, we can make a reusable one. So we say that a VGA driver is something that consists of the sync signals. So this is something we can directly connect to the screen, and also consists of the x and y coordinate of the current pixel. So this is the counting in our head. This part is taken care of by the driver, so that the rest of the circuit has to just be able to compute the color of the xy of the pixel at the xy coordinate. The reason that these are maybe values is because the timing works out such that there are lots of moments at the end of each line and also after the last line where you're outside the visible area of the screen. So you just have to wait for the next line or the next frame to start. And in these cases, there is no meaningful coordinate that we can report. So so in those cases, these signals contain a nothing value. And then the VGA driver itself is just a function that takes a specification of the VGA timings that we want and gives us back a VGA driver. So it gives us back the sync signals and the XY coordinate signals. And for example, 640 by 480 at 60 Hertz, that's a VGA timings consisting of a bunch of numbers that you basically have to look up in some online database of VGA modes that runs at 25 megahertz, which basically corresponds to, if you want to do 640 by 480 pixels 60 times per second, plus you have all this overhang at the end of each line and also after the last line, then you need to do it at 25 megahertz to accurately count where you are on the screen. And then this gives you a 640 by 480 resolution, which is tracked in the type, which is how VGA driver knows what index types to use as the coordinates. Okay, so with all this, we have our design for Pong, right? Because what we can do is we can take this VGA driver, connect the sync lines to the screen, and then look at the y coordinate to see if this is the end of the frame, which we can detect by the y coordinate becoming nothing. So the instant that it goes from just something to nothing is when the frame ends, okay? And then this information we can use to enable the register containing the state to get updated. The two inputs to update state, of course, are the up and down buttons. And then the current state is also and the current coordinates are fed to this draw function, which we have already written. So one small hiccup, I mean, it's an intentional hiccup to make it not so trivial, is that the VGA mode we use is 640 by 480, whereas our draw function was 256 by 200. But that's not a problem because we can have coordinate transformations. So center and scale are two functions that translate signals of coordinates. So scale basically turns, like a 512 index into 256 one by only taking, by changing only every second cycle. And then center puts, two bars at the two sides of the screen, so that instead of 512, it becomes the full 640, and the same vertically. And again, these are reusable and strongly typed combinators. So, okay, so this is like a nice diagram, right? But what does it actually look like when we want to code it? So what we do is we tell Clash that we suppose a 25 megahertz clock. So we make a clock with 25.175 megahertz. And then we say that the circuit itself from the outside world consists of 4 inputs and 1 output. So the 4 inputs is the clock, a reset line, which it's like usually either a button on the dev board or the clock generator will give us some reset line. And then the other 2 inputs are the 2 buttons. And then the output is the VGA connector. So this really, describes the fact that our circuit is a circuit from 2 buttons to a video output. So the active high type is there because in a real electronic hardware, a button might be active low or active high, meaning that if you press the button, does that mean that the voltage goes from low to high, or does that mean that the voltage goes from high to low? Both of them are equally valid. So here, because this is for a particular dev board that I use, which happens to use active high buttons, so we use this active high type here. If we use the bool, that would be very confusing, because if it was active low, then but we use bool instead, that would mean that true means the button is not pressed and false means it's pressed, which which would lead to all kinds of bugs. So instead of this, there's this from active function which knows about the type level polarity, and if it's active high, then true becomes true, but if it's active low, then false becomes true. Okay, so then the board itself is a function from the 2 inputs, so the up and down buttons, to the VGA output. So the VGA output consists of the VGA sync, which is given to us by the VGA driver, and the current RGB value. So what is the current RGB value? The current RGB value we get by drawing the current state and the x and y coordinates. So x and y coordinates, as we can see, are scaled and centered from the raw video coordinates. And then, if we're outside the 256 by 200 scaled up situation, then we just draw a border of all black, as we will see shortly in a screenshot. And then the state itself, well, it's a register that's initialized with the initial state, and then at the end of every frame, i.e. when the justness of the y coordinate falls to false, at every those instant, we update the state by taking the current inputs and the current state. So this is the full Pong circuit, and what I would like to stress here are the bold parts. So you can see that make inputs is the constructor that we made previously for our state type. Init state is the same value of type make inputs that we wrote initially for our software version. Update state is the pure function that we wrote for our software version, and draw is this shader or pattern function that we wrote for our initial software version. So everything else is just there to connect the buttons and to connect the result of drawing into the physical screen. So everything that is Pong specific, we can share with the software version, and that's basically what that's what this talk is about. The fact that we can do that if only we structure our programs and also our circuits in a certain way. So we've seen high-level simulation where we just took the software implementation and just ran it as software Haskell. So what about lower-level simulation? What if we want to simulate the circuit? So usual way of doing that is basically batch simulation, where you write some generator of input signals, and then you run a simulation, you get some output signals, and then you look at that. But that's lame. That's not what we want. We want to play Pong, right? So can we do interactive simulation? And it turns out we can, because Clash has a simulator built in. So Clash can take a signal, Clash can take a circuit and run it. And there's a way to run it in such a way that you simulate it clock period by clock period, which is exactly what we need, because this way we can simulate for a bunch of periods so that the full scale, no, so it doesn't. And so there's a question whether scale does division. And no, because we don't want to do division in hardware. That's super messy, if at all possible. So what scale does is, so scale is not a pure function. Scale is not a pure function from coordinate to coordinate. Scale is a function from signal coordinate to signal coordinate. And what it does is it internally keeps, semantically it is. But implementation-wise, it internally keeps an extra count. So when the input changes that many times, only then the output will change once. But yes, semantically it is a division of coordinates, but it's not implemented as such. Yes, so we have this period-wise simulation, which means we can do I/O between clock periods. So we can sample the keyboard state and we can draw the result. So how do we draw the result? So remember that this is now a full circuit, so we don't get like the pattern function, we don't get a description of a mapping from coordinates to colors. We get the VGA signal, which is like this serialized stream of colors. But we can write in Haskell a VGA signal interpreter. So we can write a VGA interpreter that detects the sync line changes and uses that to figure out, where lines start and end. And so this way we can draw in a window what we would see on a real VGA screen. So here we can see that this is not exactly what we had in the software version, because we have this black border around it. So the reason for that is because, remember, this is a scaled up by 2, so 256 by 200 scaled up by 2, that's 512 by 400. That's not 640 by 480. We have slack and we centered it. So outside that area, we need to we draw black because the circuit, remember, had this this width border call. So that's why, and here we're interpreting the full screen. So we don't even know, like the VGA signal interpreter doesn't even know which part of the screen no, it's not built into Clash. It's just a library that I have. So I get to that at the end of where everything is, but basically it's just a Haskell library. I answered that question at the end. So, but one problem with the Clash simulator is that it's not very performant. So I get about 1/3 frames per second if I simulate it with Clash. But we can get better performance with Verilator, which is a off-the-shelf open source Verilog simulator. So what we do is we can generate Verilog from Clash, which is what we would do anyway to feed it to the FPGA toolchain, and then give it Verilator. Verilator gives us a performance simulator, and then we FFI to that. So I have a package called Clashilator that automates the FFI to Verilator. And And that way we can keep everything else. So the VGA interpreter, for example, we can keep that written in Haskell, and we just use the very later simulation as like the core that we run in this hot loop. Okay, so this is how we do the simulation. So now what about actual hardware? So like I said, the basic workflow is that you run Clash to compile your Haskell or your Clash code. Yes, it is basically a software version of a capture card. So you run Clash to make to generate Verilog, and then you feed Verilog to your FPGA vendor tool to make the bit stream that you use to configure your FPGA. And so Clash Pong itself comes with a turnkey build system using Clash Shake, which supports basically 4 different tool chains. So there's the old Xilinx tool chain, the newer Xilinx tool chain, Intel Quartus, which was contributed by Dylan and Alexander, and also it supports SymbiFlow, which is an open source, like reverse engineered tool chain for Xilinx 7 series FPGAs and also other families of FPGAs that I haven't had the opportunity yet to play around with. But with Xilinx 7 series, I was able to get Pong working like fully open source end to end, which is great. SymbiFlow does have some bugs, but it's actively being worked on. And maybe you could contribute your support for your development board. It shouldn't be too hard. If it's one of these two chains, then it's a simple matter of just adding a bunch of configuration entries into the shake file. If it's a completely different tool chain, then you have to look at the existing shake code, I guess, and figure out how to proceed from there. But it would be nice to bring this to many different development boards. And at this point, I would have a demo video, but I think it's easier if I just link to it afterwards. But basically, the demo is just me uploading to the FPGA and then pressing a bunch of buttons to move the pedal around. We'll see if we have, okay. So the title of the talk promised that you can get all 3 of Executable, Synthesizable, and Human Readable. So let's see if we managed to do that. Well, what we wrote for Pong is executable because most of the code, if we just throw away the code that connects to the physical buttons, everything else can be compiled as plain software Haskell, so we can execute it as a very high-level simulation. But at the same time, it is synthesizable, so we can take that same Haskell code and feed that to Clash and then get an FPGA configuration, so get real hardware at the end. And it is human readable because we were able to use idiomatic Haskell, like lenses and whatnot. We can make reusable components such as the VGA signal generator with nicely and strictly typed, strictly is probably not the right word for it, like tightly typed APIs. So we can use the full power of Haskell when making hardware. And so this is basically the end of the Pong example, but there's a lot more to read if I got you interested in this, because I have recently published the book Retrocomputing with Clash, Haskell for FPGA Hardware Design, which is basically all about the same approach of writing hardware with a Haskell first mindset. And it contains full implementation of various fun retrocomputing devices. So one of the goals of the book is that it's not just dry and theoretical stuff, but everything, all the abstractions we build are in service of some fun circuit that we build in some later chapters. So we build stuff like, Pong obviously is one of the examples, but we build like a computer that uses brainfuck as its machine code. we build an Intel 8080 processor, and by the end of the book, we build a full home computer from 1977, I believe, which is compatible with the original one, and we can just like run the original software on it. So if you want more details, you can check out the book. And also, so this is now where I answer the question about, is the VGA interpreter built into Clash? So if you go to the link here, there are links to all the repositories on GitHub for the code in the book, and also the utility libraries for stuff in the book. And so the VGA interpreter is in a package that's, I think it's uploaded to package now, called Retro Clash Sim, which contains a bunch of simulation utilities, but it's just normal. It's just written in Haskell. It doesn't need to be built into Clash, and it doesn't even know about Clash, because it's just a stateful sync. It's just a sync of VGA signal values, clock period by clock period by clock period, and every now and then it spits out a frame. So that's how it works. And yeah, that's basically it. Thank you. I see that I managed to fill in the 1 hour, which is fun, because this talk was originally for like half an hour, of course, with much less detail. So thank you for your attention. I know that you're not going to be able to rush home and immediately, without looking at anything else but the slides, immediately start programming FPGAs. But I think if you pair it with maybe like some reference documentation, you should be able to take the idea away of structuring your circuits in like this Haskell first perspective. So yeah, thank you, and of course I'm open to questions.
Yep, Gergo, it was awesome as always, hugely impressive. We had several questions. Let me pop in these. So there's one here.
Yes. So yeah. So it's a third party. I mean, well, I guess second party, because I'm the party in question. But yes, it's not built into Clash. It's by me.
Okay. Here's the next one.
Right. So that's a good question that I don't have a good answer for. So on one hand, so Clash's model is that it will never put in a register where you didn't put in a register in your code. So there's a direct correspondence between the code you write and what comes out in terms of the combinational structure, or like the RTL structure. But if you want to go down further, then the fact that there are all these abstractions could be working against you. So for example, if you add two, let's say, 10-bit signed numbers, the details of that, of how they are going to be added, is beyond your control if you use Clash and you use 10-bit signed numbers. So and if you instead just use bit vectors of width 10, and then you write your own function that twiddles with the bits in the way that you want to implement addition, then maybe it will give you a better circuit. So it's up to you where you draw the line. You can go down, so you can write everything in terms of n-bit vectors, but you kind of lose the point of using Clash at that point, I would think. And you can do that on just the small parts that you think are like on the critical path, or thing that has many copies on it. But yeah, so I guess the short answer is the more abstractions you use, the harder it's going to be to know exactly what the generated circuit will be. But at least on the RTL level, it will always have the same shape that your Haskell code was in.
Okay. There's one more question for you.
Yeah, so the Pong game runs at, say, 50 hertz. Oh, no, so the... Okay, wait, let me bring back the slides. I accidentally... I think I closed them or something. Okay, so yeah, so the game... Okay, so let me go back to the slide with the schematics. Yeah, this one. So Pong game doesn't like run at 50 hertz as a random rate. It runs at the frame rate. So Pong updates the state at the end of every fully drawn frame. So the way we do that here is that we use the y coordinate that we get out of the VJ driver to detect when it's the end of the frame, because when it becomes nothing, so it used to be a just value, now it's nothing. And it's going to be nothing for a while, because the vertical retrace takes time. But when it becomes nothing, then that's when we know that we should update our state. So we feed the frame end signal as the enable line of our register that holds the state. So here you can see that ST, the signal that is the current state, is defined using this reg-n combinator, which is a register with an enable line, and the enable line is frame end. So the state transition is only enabled when it's the end of the frame, and it's the end of the frame if the justness of the coordinate is falling, if it's becoming false.
Awesome. Well, thank you very much, Gergo. It was, as always, hugely impressive. I can't wait to get my hands on that book.
Thanks.
Thank you very much. And I just wanted to tell you guys that we're going to have more online sessions pretty soon. So we are aiming at one talk a week, which is a pretty tight schedule. And we're always looking for new speakers, especially, and also people who would like to share their experience of what they're doing with functional programming languages. We're open to any language, so please bring your suit and tell us about your work, what you're doing in your free time or whatever. And we hope to be playing a good part and continue our 160. This is, I think, our 160 some number 160 something meetup. So we had a huge amount of meetups in the past. Unfortunately, we had to take a short break, but now we are back fully online. But I definitely hope to see you guys in person, and a huge thanks to everyone who joined in today. And the video is going to go out on YouTube, and definitely there will be many more people watching this, hopefully over the coming weeks. And Gergo, thanks very much again. And,
yeah, sorry, if I can just add one more thing, because you mentioning video reminded me that there is something that I didn't show, which is the video recording of the whole thing in action. So right. I think, yes. So you can see this is the dev board I've been using. Right. So you can see there's a VGA connector on one side. There's a USB cable that goes to the computer that we upload the configuration from, and then we have a bunch of buttons there. And that there is the FPGA itself. So now I'm going to turn it on, and then there's some default configuration. Oh, hang on. I think it froze for me, or
it looks like your camera feed has died.
Okay. Well, I something must have happened because I can't see the video. But anyway, what you can see in the video is that I upload the configuration, and then it starts playing Pong. I can't see the video now myself, but actually, I don't even know if you can hear me.
But Gergo, you mentioned that you have a link to this demo video, right? I mean, I know you were just recording your camera just now, but you have a video on YouTube that you could share
yeah,
the link
yeah.
to. Yeah, so we'll tweet that. So you guys just please keep an eye on the Twitter feed. All right. I think Gergo's machine just crashed. So I want to thank you guys for watching, and we'll see you guys next time. And Gergo is back, so I'm just going to bring him back. Hey.
Yeah, I'm not sure what
Lost him for a
happened,
sec.
but yeah.
All right, so huge thanks again. We'll post the link, and thank you guys. Thank you, Gergo. It was all massively interesting and intriguing. So we'll definitely be seeing more of this in the coming weeks. So thanks, guys, again. Thanks for watching.
Yeah.
Thank you, Gergo. And you
Thanks
guys
for having me.
have fun, and see you soon.
Bye.
Bye guys.